Okay, so last time we started all the shop for the times 2 times 3 problem, and the idea today is to continue. Good. Oh, good. I can see you there. Right, and good. So let me remind you what is our setting. We have A and B, two commuting matrices, 3C, integer coefficients. We consider both of them as diffeomorphisms of C3. They preserve our measure. We have the C-square action on automorphisms of T3, which is alpha of nm is a to the n, b to the m. I didn't say they commute, but they do. And we are making some assumptions that imply that we have this splitting. Rn is E1 plus E2 plus E3, and three associated exponents chi I and n is 3 from R square to R, which are the extension of the guys. So we have that alpha of n is e to the chi I plus minus n, time bi is this, for bi is in this space ei. So inside these eigenspaces, this is how the corresponding matrix acts. And n is in C square. Now, so that's are the very basics. So we do then the corresponding suspension m alpha equals to R2 times T3, quotient by the relation, where Tx is related with T plus n alpha of n inverse times x. So this is a 5-dimensional manifold which has fibers equivalent to T3, and it fibers over T2. And on this M alpha, we have this R2 action, we still call it by alpha, that projects into the corresponding R2 action on T2 by translations. So the R2 action is alpha of S applied to Tx is nothing but T plus S x. And in the gluing is where actually dynamics. So you, as always, you never see anything happen in the second coordinate, but it's the gluing that is really things happen on this second coordinate. Now we have these spaces called Wi. So for P, in M alpha, we have these spaces Wi of P, which are tangent to Ei of P, which is actually inside the fiber. So these guys are the associated guys in in T3. So this is naturally identified, not completely naturally, but is reasonably identified with R2 times R3, and this R2 times R3 has a splitting R2 times E1 plus E2 plus E3, and this is the EIs. So these are what we call the EI of P. So even though this identification is not completely natural, the invariants of the splitting tell us that the E1, E2, and E3 are well defined on this space. So maybe I should talk a little bit about this identification before I continue. So observation. So M alpha, the universal cover of M alpha is naturally fairly well identified with R2 times R3. Maybe let's just still use identification here. So because it's the quotient of R2 times T3 M alpha, and so the covering of R2 times T3 is R2 times R3. Now this identification is not fully unique because you have the natural transformations on M alpha, which is T, well, you have two types of transformations. Let me denote Tn of Tx for n in R2 is the guys used to glue, which is T plus n alpha of n inverse of x. So this is one type of transformations. And the second type of transformation are L sub k, oops, this is C square, not R square, of Tx, now k is in C3, which is Tx plus k. Okay, the translations on T3. So when we quotient by these guys, which is a copy of C3, I get the torus T3. And then if we quotient for everything, then we get M alpha. Now, I have this group C square, this group C3, but these guys do not commute. Okay, actually they form a solvable group. This guy is normal in this guy, if I remember correctly. One is normal in the other, I think, yeah, is this guy normal in this guy? But anyway, so that's what you get. And what is important is that you still have this group, which is the fundamental group of M alpha, which is just put this transformation group, join with this transformation group, they form a group, which is C squared semi-direct C3. And this is the fundamental group of M alpha, which is not abelian, and more important, it doesn't act by isometries of R2 times R3. So these guys are isometries from R2 times R3, but these guys are not isometries. So these are isometries in the second coordinate and also in the first coordinate, because you are doing nothing in the first coordinate. These are isometries in the first coordinate, but are not isometries on the second coordinate. So since this is what is happening, it means that the standard Euclidean metric in R2 times R3 will not descend to the quotient.
But why are they not isometries? They're SL3Z matrices.
Yeah, but these are not isometries. They preserve volume, but are not isometries. Yes. So they still preserve volume, but they are not isometries. So the effect of this, and it's important for us that they are not isometries, is that our action, R2 action, alpha of S, is not isometric. Okay, because the way it looks like is isometric in the first coordinate, which it is, because there is a good isometric structure in the first coordinate, but it's not isometric on the second coordinate. This is fundamental for our game. Yet, this E1, E2, E3, so this space is 0 times EI, are preserved for both guys, for the derivative of both guys. Okay? For these guys, because they are just translations, so the derivative is identity, so nothing happens there. And for this guy, in the first coordinate, you don't care, you have a 0. On the second coordinate, you have the alpha n, and the alpha n preserve these spaces. So they are preserved, which means that I have a well-defined, and that's what I wanted to stress, guys like that. Okay, that's essentially all I wanted to observe and stress. Now, typically, what we do when we try to speak about Riemannian metrics or things of this sort in this space, we restrict to some sort of fundamental domain, which is just the 0, 1, even open here, square times R3. So the first coordinate is a fundamental domain for this guy. The second coordinate, these transformations are not really making any trouble. And then you do whatever structure you want to put there, and you translate by these Tn's to all the rest, which is what you do typically in any manifold when you want to put a structure coming from the universal cover. Or you can do it directly downstairs, but I think that's a good way of doing it. Okay, so we have the WIP, which are essentially the same IAIP but projected. So we can even be very precise now that we have all the structure. So WIP are the points of the form. So P here is of the form Tx. These are the points of point T, X plus Bi, such that Bi belongs to EI. Okay, so that's a very precise definition, and I should put here the vertical brackets. And of course, one should show that this is well defined. Okay, so independent of the choices of Tx. But the fact that these are well defined is more or less what I said about being invariant by this alpha of m. Okay. So we have these guys, which are tangent to the corresponding space EIP, which is the translate of EI over P. And we have our lemma describing the dynamics from this perspective of the WIs. And this is this lemma. Saying that we have HI P from R into WIP. Actually, I could put R or I could put EI. For that matter, it's not much of a difference. Let me put EI. It's a little bit more natural. So diffeomorphisms, C1 diffeos onto its image. Actually, this is, so here P is, let me put T naught X naught. So this is the diffeo, it's already written there essentially. So if you want to do it explicit, is of VI is T X naught plus VI. So that's the precise definition of the diffeo. There are such that one, the dependence on P is continuous, where this guy belongs to alpha and this guy belongs to embeddings, C1 embeddings from EI to M alpha, or immersions, maybe it's better than embeddings, it doesn't matter. Well, it's topology of convergence on compact C1 convergence on compact sets. is the topology here. Second, yes, well, it's a matter of definitions. So yeah, you don't want self-intersections and everything, but the space of embeddings have the same topology as the space of immersions, for that matter. So it's a subspace of this and have the same. So sometimes embedding, you want the topology of the image to be the inherited topology, and this will not be the case here. And then it's just a subtlety. That's why I'm putting immersion. So it's an injective immersion. It's not so important. Now next is the diagram commutes. So what is the diagram commuting? I'm going from Wi of p into Wi of alpha s of p here. Here I'm going with hp. Here I'm going with h alpha of s of p. Here is the map alpha of s, so it's the flow is mapping this guy to this guy. And in the coordinates E, what I really think is multiplication by plus minus, and I said I'm going to forget about the plus minuses, so I'm doing it right now. So you assume that eigenvalues of the two matrices are positive. So here we have by e to the chi I of s. Okay, and here s is alpha. And this is essentially automatic from the definition. Okay. Now next thing is here.
And by the way, so these HIs are actually C infinity.
Yes, yes. We only care that they are C1, but they are C infinity even real analytic. If we put the natural real analytic structure on M alpha, they are real analytic. Yes, and most of the time, in whatever theory we will do, they will be quite smooth. So most of the time, as smooth as the alpha action. But yes. So these are called affine coordinates. So HIP are called affine coordinates, or, well, actually they are called, let me put a different name. So normal forms, and actually, due to the third condition that I will write down, they will be called also affine coordinates. But so far they are normal form because they give a normal form to the dynamics, which is multiplication by a number.
And the tangents of the WIPs will be precisely EIs.
Yes, yes.
As they're embedded in the...
Yes, exactly. And sometimes we call this the fiber dynamics because the dynamics happening on the T3, which is the fiber of the M alpha going. So the third condition is the change of chart. So if Q belongs to Wi of P, then I go with P, I go back with Q. This goes from EI to EI, and I get that this transformation, we call it HPQ of BI is BI plus some PPQ for some TPQI in EI. It's just some translation by number, and that's why it's called an affine structure. Actually, it's a translation structure, but we call it affine because in the more general situation, you will have something maybe here multiplying, and so this is an affine map. But whenever you can put a family of charts on a manifold whose change of coordinates is affine, it's an affine structure on your manifold. Okay? One more thing I wanted to say. Yeah, even in the more general situation, these normal forms, we have a structure a little bit weaker than this. So this change of variable will have some group structure. So will be some polynomial preserving some structure, and then you will get some solvable group structure still on these WIs. And that's very useful for the general situation. Most of the time, and in the setting we are working here, all this is very natural and simple, and you are just inheriting the structure of EI, putting it into the WIP, and when it goes to the SL3R, like in Margulis' normal subgroup theorem, everything will come naturally from the group acting. Okay, pretty much like here. So everything is algebraic, so all these guys. And again, the fact that this is true just follows from the very definition of this. There is not much more to say about it. Okay. So maybe one more observation here is that if S belongs to the kernel of chi I, then in these coordinates, what I get is just identity and nothing else. Okay? Okay, so now let me draw a picture of how to think all these localized pictures working together in the global dynamics. So we take P in M alpha, take some S belonging to the kernel of chi I, so here is P. Inside P I have this WI line, which is inside of T3. So let's say P, it's not really important this writing, but is T naught times X naught. So this T3 is T3 to P is T naught times T3. So it's this fiber over T naught. So inside this T3 I have this guy. And now I flow. I consider alpha of L times S from M alpha to M alpha, L some integer. Actually, some real number is. So this is L times S. So I have this S belongs to R2. So this is a time space. This is the kernel of chi 1. So this is S. And then I'm moving L times S in some direction over there. S not 0 because S equal to 0 will not move at all. And then I'm looking to these dynamics. Now, when I restrict to the Wi of P, mapping Wi of P into Wi of alpha Ls of P. So I start moving this guy. So this is WIP, is contained in T naught times T3, and I flow. Here is alpha Ls of P, here is its Wi, which is actually inside T naught plus Ls times T3. Okay, and of course this should be understood as a mod 1 business. So it moves. Now, observe what I said long time ago. This direction is irrational. Okay, so in the bottom of all this, we have this dynamics on T2. Which is the time dynamics, in a sense, the group dynamics. And we have these flows, T naught plus Ls. So here is T naught. And I have this flow here, this irrational flow. And here is this nu dot T naught plus Ls. Now, since I assumed that, and I know that S is irrational, if S is not irrational, it's the same for that matter, because it's a nice dynamics in the base, I have that in the base I'm coming back to T naught. Okay? Which means that while I keep on flowing, this point will come back very close to somewhere in the T3 that contains this P. May not come close to P, may not come close to anywhere here, but it will come close to this torus. In the case this were irrational, actually it will come back to the very same torus, so it's even better. Now imagine for a second that I manage to have a Q there, and imagine alpha Ln S of P goes to Q for some L sub n. Imagine these were true. I don't know if this is going to be true at all. Imagine these were true. Then I have this sequence of transformations. Alpha Ln S from WIP into WI alpha Ln S of P. And this will have as a limit, because these are always isometries, okay? This will have as a limit some map from WIP into WIQ. So it will be an isometry that brings, because that's the property of each guy, so each guy here is bringing WIP to the P to the alpha LSP. So in the limit, I will get that P is bring to Q. Okay, so what I get in the limit is a map from this line to this line that brings P to Q, and it's an isometry, actually it's a translation. So by doing this limiting argument, I built dynamically a translation that moved from P to Q. So of course the translation from P to Q existed, it's not a very big deal, but I built it dynamically now. So as a limit of iteration of our dynamics. So this will be crucial for the next thing, which is understanding the conditional measures along this WI direction. So that's what we have to build now, the conditional measures along this direction. So remember that all this is about some measure we have to understand, and we are going to try to understand the conditional measures along these WI directions of the measure.
Recall that this time, but I think last time you said that WIPs are contain some P.
Yeah, WSIP are also continuous in P. Yes, that's also important. Yes, which it is an important fact. So it follows in this case from the definition essentially. But yeah, in a more abstract situation. So again, in Margulis also is not so much needed, but in the very abstract situation, yes, it's one extra item. Thanks. Okay, so now conditional measures. Yes.
But if we have chi is not zero, then that doesn't happen.
The chi not zero? Yes, actually it happens most of the time. So I have this Weil chamber picture, and if I'm not over this line, here the chi of S is different from zero. Okay? So
the maps don't really converge.
So for, yeah, exactly. For if I'm not over this line, there is, well, if chi of S is positive, then I will have complete divergence. If it's negative, then everything will go to the constant map. So you have convergence on compact subsets to the constant map. Everything concentrated. But again, both ways I lose information, because if I collapse everything, it's not telling me anything. And the whole magic of this theory is the fact that I can make this guy zero, and I have this passing of information when it comes to infinity. So I can send time to infinity and make this transpass of information from P to Q, which is what you cannot do in most of the case in hyperbolic dynamics. Because exactly that. So in the hyperbolic dynamics, you have either contraction or expansion. So in the expanding direction, things diverge, and then you are losing information. So the information around P is getting away from P, and then when I get to the limit, I'm not able to transpass this information around P. And if you have contraction, then, well, everything goes to zero. And then, again, there is not much information, just P telling what's happening with P. And again, nothing happened. While here, since everyone is going together, I get that all the guys here, all what is going on here, so all the structure here is the same as the structure here due to dynamics, assuming that you are talking about things that are invariant by dynamics. And then at the end of the day, this has a limit here. And if you have a continuity of your information, then you get into Q. And then whatever thing that was invariant by dynamics is also invariant by this transformation that moves P to Q, which is a translation. And that's the whole point. So the object that I want to be invariant is this conditional measure. This conditional measure then will be invariant by translation. And we know that the measure invariant by translation is hard measure. And that's how is the proof that conditional measures are invariant by translations. And once you know that conditional measure is hard, then a little bit of more effort gets you hard everywhere. Okay? But this a little bit more effort needs to be established.
So are you going to prove that imagine statement? Or
which one?
The imagine as limit.
Yes, this imagine is, I'm going to prove this imagine. So this will become a proposition that you don't need to imagine, it actually happens. But yes, it's one of the hardest and indeed impossible facts when you try to. So the difference between Katok-Spatzier or Rudolph and the Fields medal on Lindenstrauss is in the way you can prove this imagine. So Katok-Spatzier and Rudolph need a very strong hypothesis to prove this imagine, which was not present in the setting where Lindenstrauss, Katok, and Einsiedler were working. And well, being able to do that, this gap is a fields method. So yeah, it's what is called the pi-partition trick that I will discuss. So even this, which is supposed to be the easy case, is very hard. And it has to do with this fact I already discussed, the fact that every direction is by itself the unstable direction for some element of the action, plus some other facts which I'm going to discuss. Okay. Okay. So let's discuss conditional measures in this setting. So now I need to decompose the measure mu. So we have a measure mu on T3. We build a new measure mu bar on M alpha. It simply is very much similar to what we did when we did the suspension G times M or G times X mod alpha. So let me just do it briefly. I will not go through details here. So on R2 times T3, we put lambda times mu and project to M alpha. Or if you really want the details, we take on this fundamental domain, we take lambda times mu, and then this is a bisection with M alpha, and then you put this measure on M alpha. And this is a probability measure there. So this is probability. Okay. So we have this measure. On there. This measure is alpha invariant. It's not important, but not for the construction I'm going to discuss here, but it's important in general. So mu bar is alpha invariant. And have in mind, just if you want examples of what we are talking about, is mu could have been Lebesgue on the torus T3. So this is Lebesgue on this M alpha, and everything is invariant. The other possibility is that mu could have been delta at 0. 0 is a fixed point for the action. And in this case, this measure lambda, mu bar, is essentially supported on T2, on a copy of T2 over this T2 on the base. So it's T0. So it's this copy of the torus T2. Okay, and it's Lebesgue measure on this copy of the torus T2. That's mu bar in this example. And if you have a periodic orbit, so a finite orbit for the action, then you will have some torus still. Yes, you will have some torus that covers the torus T2 from the base, and it will be Lebesgue measure over this torus that covers the base.
Is it true that any measure on M alpha that projects to Lebesgue is also important?
Nope. You have many more measures that protect to Lebesgue because you are, if you don't require them to be invariant by alpha, you have really a lot of things. And oh, you mean? No, you still can take, so you apply Rocklin decomposition to this game here, and you take whatever family, measurable family of probability measures onto tree. So you take any measurable map defined from here into here. So lambda almost everywhere defined, and then that's all the possible probability measures. So integrate then this dx, and these are all the possible. That's, yeah, this is yet another application of Rocklin decomposition, which is a very powerful gain. Okay, we have this measure. Now we have this partition Wi of p in M alpha is a partition of M alpha. Now the problem is that it's not a very nice partition. It's not what is called in a measurable partition or a countably generated partition. And the reason for that is because the WIP are all irrational lines on the torus T3. And this is like making the quotient R3 or T3. So the quotient space is like making this quotient space, which is as bad as R mod Q, and is very bad quotient space. So this is not a Lebesgue space, is not isomorphic to the interval 0, 1 from the Borel perspective, from the sigma-algebra. So this is not a very good partition, yet it's a nice foliation. And what is very important is that it's locally trivial even in the long range. Okay, so lemma also there exists Kn contained in EI, Kn compact, we call them Bn rather than Kn. Bn contained in Bn plus 1, the union of Bn equal Ea, and Bn actually, for that matter here, Bn is ball of radius n, centered at 0. That actually is not so important. Okay, the point is that I can exhaust EI, and then I have that for every P in M alpha and every N, there exists a neighborhood V and P a neighborhood of P such that B and P, actually the transformation, maybe someone else, and some sigma contained in M alpha, sigma transverse to WIP, so 4-dimensional manifold. It's not really important that it's a manifold again, so this can be actually make it much more abstract into a measurable category. What is important is that the natural map iota p from sigma times Bn into Bnp iota p of sigma V equals to essentially sigma plus B. For the plus B, I mean what I mean before, so maybe let me make it more explicit. So this is sigma is sigma 1, sigma 2. So this is the class of sigma 1, sigma 2 plus B. Okay, so is this embedding there. This is a homeo. It's actually a diffeo, but I want this to be a bisection. I want it to be injective. So let me draw the picture of what I want with all this writing. Here is P. Here is the Bn going through P inside Wi of P. Here is sigma, some 4-dimensional manifold, and I now for every point here just draw the line here, and this is going from sigma times Bn into the manifold. And I want this to be a homeomorphism. So it's a local trivialization of this BWI foliation, but also for the long. So this sigma is very, very small when the Bn becomes very long because of the recurrence of the WIP. Okay? Okay, so that's...
So does this VP, does it contain the whole WIP?
No, 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 it's only up to the Bn.
Right, okay.
So this is, so this what I draw here is exactly the BNP. It's up to here. So actually this is wrapped out, so it comes close.
What do you mean by long range?
Yes. So let me draw a lower dimensional picture in the case of the torus T2, and instead of WIP, I take an irrational flow. So you have P here. This is an irrational line. So this goes here, and this goes here. This already comes here. Okay, let me say something that long. Then I'm taking some very small neighborhood here, and I start drawing. So I have this. This is only moving one direction. So I continue that way, and this went here. Continue that way, and if I do it small enough, they wouldn't overlap, so I cannot continue because they will start overlapping. But that long it goes. Okay, so this is the, for this length, this is the VP. If I really want to go further, then I should shorten this sigma, and then I can go further with the VP. So when it comes to flows, it's called, sometimes in some people, it's called the long tubular neighborhood. Okay, so you have the tubular neighborhood statement, which tells you that locally a flow is just the foliation, and then you have the long tubular neighborhood, which says you can go as far as you want if you give up some length. And this is the same here. So, and for foliation, it's always true. You have this long tubular neighborhood statement for foliations. So any foliation have a long tubular neighborhood statement like this. When it comes for more general partitions, it's not obvious that you have it. We want them to happen. So I want partitions of the measurable space I'm working on, which have this long tubular neighborhood statement. So which means this bisection, and of course then the partition have to be well approximated by compact partition or by locally finite partitions and blah blah blah. So it's a little bit harder to state.
And sigma is going to depend on n as well.
Sigma depends on n, absolutely. So yeah, this, well, iota. So the sigma is just, yeah, okay, yes. Certainly, yes. This, the capital sigma, yes. Yes, yes, yes. Now, this is what I need to apply Rocklin lemma. So Rocklin lemma works for measurable partitions. And then if I restrict to these guys, I can apply Rocklin lemma to these guys there. Okay, and then by applying Rocklin lemma to these guys and then doing some sort of partition of unity in a sense, or some more general partition game, I can prove the following proposition, this integration proposition, which is just a corollary of Rocklin decomposition put with all these guys. So proposition for every I, there exist measurable maps mu hat I sub p from m alpha into radon measures of EI defined mu bar almost everywhere on that m alpha, so that if mu bar IP is defined as this HP star of mu hat IP. So now I'm projecting these maps, these measures which are in AI, and projected them to the WIP. And actually what I'm going to write is almost the proof of the proposition. Okay? And so this is for P in M alpha, and if P naught is in M alpha, and this Bn P naught is as previous lemma, then I can apply Rocklin lemma to this neighborhood. So then if phi goes from Bn P naught into R, the integral of phi d mu bar is equal to the double integral of phi d mu bar n P naught sigma of B d mu bar sigma of sigma, actually sigma n as you said, or this is over sigma n, this is over, oops, wait, no, this is over sigma n, this is over y iota pn of sigma times pn. So this is Rocklin decomposition on this nicely measurable partition, and what I wanted to stress for this is these guys, these are probability measures. Mu bar sigma n p naught is a probability on this guy, iota p n sigma times pn. And now I want to relate this guy to this guy. Okay, so this guy depends on n, these guys are independent of n. Okay, I will need to go there. Just give me 1 second. Then mu bar sigma np naught is equal to mu bar p or ip divided by mu bar ip of b of I sub p of sigma times bn for every sigma, and here p equals to yp of yp naught of sigma times 0 and I guess that's it. That's all I want to say. Actually, maybe more. I can even put this times b here, and for every sigma in sigma, p is that, and I think that's it. Yeah, almost every guy. Okay, so I can do, so what is this proposition telling us? So I can do these tubular neighborhoods, local tubular neighborhoods on the manifold of the Wi's. Now, when I restrict to this tubular neighborhood, the partition by Wi's on this tubular neighborhood is a very nice partition. So and I can apply Rocklin to this, and it gives me a decomposition of the measure, mu bar on this subset. Now, what this is telling me is that all these conditional measures agree all together, independent of the tubular neighborhood, to give the same measure mu I bar. That only depends on the leaf and not actually on the tubular neighborhood. This up to some normalization. Okay, that's why I divide here by this, because Rocklin is giving me probability measures. The measures I'm getting, there is no way I can normalize them naturally. So when I make them these guys, so yeah, that should be restricted here to this guy, IP of sigma times Vn. When I restrict it to the leaf, I normalize it to make it to a probability, is the one that is given by Rocklin. And actually, Rocklin decomposition is unique, so there is an addendum about uniqueness about this mu hat. So, moreover, mu hat IP are unique up to a multiplication by a number. Okay, which means that they are unique on P of radon of EI, which is radon of EI mod R minus 0 mod R. Okay, so this is a very natural space. Maybe it's not very common, but it's getting more common by the day. So you have the space of radon measures, and you have any vector space, and you can projectivize it, which is essentially quotient by R, but it's a multiplicative R here. Okay, what you are quotienting. And this is the projectivized, okay, which are vectors modulo lengths of the vector. Okay, that is this projectivized R.
So I think my question is,
Yes.
so is it important that sigma is a four-dimensional manifold in ML, or can you just make it to be transverse in the linear model? Because EI
is important.
you want
It's what is important here. The only thing that is really important is that mu of sigma n times, well, actually that mu of B and P. This is the only thing that is really important, and actually just for almost every P. Okay? So that's the only thing that I care. And the way I define it, I get that Bn of P is a neighborhood of P. And hence, this is true for every guy in the support of P by definition of support of mu bar, and then I'm happy. If sigma n is just a measurable set, which still make this into bisection, that's all I need. Okay? So I just need this measurable partition. So the only thing I need is that take this set, and when I restrict the partition to this set, it is a measurable partition in the sense of rho. That's all I need. I don't need more than that, which is very flexible, what I can do. And actually, when it comes, we're going to do in the X alpha situation, then it will not be a manifold, because we are talking about metric spaces, and still you will have it almost for free. There are several ways of doing this part, not infinitely many, but this is more or less the more general way of doing it, which is the thing that requires less dynamics. So it's useful here that in order to define this mu, we didn't require any invariance by the alpha dynamics at all. Okay? So that's useful. It's not 100% needed in this situation, but that's very useful. Wow, 337. Okay, we went over time, but I finished with the conditional measures. Okay, so next time we will go on to use these conditional measures together with this picture over here, because now I have measures on these lines. And then I will do what I said. So I will push these measures over here and then see recurrence, how they come back here. Okay, but for this, I need to have some properties about these measures of invariance when I iterate them, and then I have this imagine business there to discuss. Okay, very good, thank you. See you on Wednesday. Hi everybody. We are here. So last time we discussed these conditional measures for non-measurable partitions. So now the plan is to make use of them. Okay, so we have, let me remind you a little bit of the setting. So we have m alpha, which is r squared times the torus T3 quotient by the relation. Alpha is an action from which is automorphisms of T3. Actually, if I want all the automorphisms, I should put a GL here. Really just affect determinant plus minus 1 instead of determinant plus 1. It's not so important. We further made the assumption already that alpha of 1, 0 is A, alpha of 0, 1 is B. They commute because of this, and we assume that this has real positive eigenvalues of modulus different from 1. So out of it we had these foliations Wi of P, which subfoliate this fiber T3. We had mu, the alpha invariant ergodic measure. These Wi's are tangent to some spaces EI, where this decomposition of R3 is inherited by the tangent of T3 in the fibers, and this leads to these decompositions. And we have this mu pi radon measures with a bar, I guess, was no, with a hat or with a bar. Oh, I don't remember. Actually, mu bar was the measure on M alpha. Mu was on T3. This is radon measures. On WIP. Yeah, now I'm having.
These were the forward measures by HI.
Exactly. So we.
I think we use mu hat.
Mu hat for the push forward. Okay, good. So we have mu hats here, and we had also mu I bar measures, also radon measures on EI, which is just, this is done through the parametrizations, affine coordinates, linearizations of these guys. We have several properties that we already discussed quite a bit. Now, the way we define, actually, and so the main property of the lemma of existence of this conditional measure in particular tells you how to define these guys, and automatically tells you that these guys are only well defined up to a multiple. So if I multiply these guys by a number depending on P, they also have determines a family which does the same game. And we have uniqueness of this family of measures up to this normalization. And the uniqueness is inherited by the Rocklin theorem. So what's the outcome of this uniqueness of this guy is a very important property. Maybe I go up. Yes. Someone erased. Okay. Is that alpha S star mu pi hat is mu alpha S of p I hat for almost every p, mu almost. Okay, so it's the invariance or equivariance of this family of conditional measures, and the reason for this, let me just put one sentence as a proof, is if I take this measure here and I apply the Rocklin decomposition theorem in this version of Radon measures to this guy, the conditional measures are nothing but this alpha A star of mu p hat I. That's the naturality of the construction. But by the same token, since this guy is the same as mu hat, then you need to have that this is the same. Well, actually, to be more careful, that's what actually you get. So you get that the decomposition is exactly this, and the decomposition for this is that these guys coincide, and then this is true. Now, for this to be true, actually, I should put a different symbol, not an equality, and it's this symbol that people use. It's like an infinity, but without things, which means that you get equality on these projective Radon measures. Okay, so, and let me put here the IE. There exists C of SP, I of SP, such that alpha S star times mu hat. Okay, so so up to a multiple, this is a positive real number, which does this game. Now it's very easy to check that this actually is not that we are going to use it at all, but it's nice information that this log of CISP, log of CI, if you think of this from R2, which is the group acting, times M alpha, which is the space, into R, this is a cocycle over alpha. Okay? So if for whatever reason you know that this cocycle is homologous to constant, so constant independent of the p variable, or even fully constant, so fully zero, then you can pick a normalization of the mu hats that will make this here into something that is independent of p. Okay? And at the end of the day, we are going to be able to do it. But at this stage, it's not possible. This is just measurable, not better than measurable. So, and it just comes from the measurability of this mu IP. So yeah, maybe that's a good observation. So P into mu IP is measurable. And The same with the bar, actually. So it's, and this actually helps us a little bit of on understanding what is this value, because we have that CISP is nothing but mu I p on alpha s inverse or alpha minus s of I over mu alpha sp I of I for every I inside W I on alpha sp. Okay, that's just because this formula is holding. So the fact that this formula is true tells you that if I evaluate in an interval here, it's the same as evaluating in an interval there. And it's independent of the choice of the interval. And then, of course, I need the denominator to be positive for this to make sense. Now, if I take I is an interval, or it's a neighborhood of P, then for almost every P, this will be positive, because for almost every P, P will be in the support of this measure, and being in the support means that this is positive. And in particular, I can just take the ball of radius 1 around P as an I, or around alpha s of P, actually. Okay. So then for almost every P, for this choice, this is positive, and this actually proves the measurability. But it proves a little bit more, which will not be really necessary for what we are doing probably, but it's useful for other situations and in general to understand how things go. So these are measurable functions. At some point we are going to take a losing set of continuity of this measurable function mu hat. And once I make this choice, automatically for the same losing set, this Ci will be continuous. Okay, because here everything is continuous. Well, as soon as I take the S so that also this guy also belongs, so that numerator and denominator belongs to the losing set. I, of course, could take yet another losing set, making this guy continuous, but it's useful to know that how is this set working. Okay, good. Now, let's see what's the outcome when I work instead of the mu hat, when I work with the mu bars. Okay? So, actually, this should have been hats, not bars. We got hats in the manifolds, and bar is in the abstract spaces. I could do all the work in the manifold, but I like actually it's more symmetric to do it on the manifold, but the cool people say that it's better to do it on the EIs. And it actually looks nice when you do it in the EIs. But anyway. So let's see this formula. What becomes of alpha A star mu hat I p? So what is this? I claim that this is the same as L, I hope I'm being consistent with notation, e to the chi I s star, oops, it should be, still hat. Now I see this in coordinates, so I apply H in alpha sp I. So I look at this in coordinates and I claim that this is the same as doing this star mu bar pi. Am I right? This should follow from the formula. I probably should have put it here. HPI alpha S pi compose alpha S is multiplication by e to the chi I of S compose, oops, okay, no, that's wrong. Here is L e to the chi I S, and this is the same as alpha of S compose HIP. So this is the parameterization. What does it? Takes the alpha S dynamics and make it into multiplication by this e to the chi I S there.
This is this affine coordinates.
This exactly. This is affine coordinate. Now this plus this formula well, this one here actually, or equivalent this for that matter, should tell me on one hand that when I push this, let me draw the picture because I get really very lost without pictures. So I have WIP, I apply alpha S, here I have WI alpha S of P, here I have the measure mu hat IP, here you have the push measure. Where is the push measure? Where does this push measure live?
Well, I think the order there is wrong on the left-hand side.
Yeah, unless I put the star upstairs, you are right, no? So I should put a minus here. Because this alpha S goes, or I should put the alpha S here rather, no? No, I think it's correct.
I think you're pushing forward using alpha S inverse. No,
No, I think it was.
okay.
So let's see the picture. Let's say it again. So if I have this alpha S from here to here, measures go back. So if I have a measure here, I'm allowed to define a measure there. So the measure here is mu I alpha S of P, and then the measure I'm having here in the picture is alpha S star of mu I alpha S of P. So this is the natural way the measures are pulled backwards or forward, and well, it happens to be equivalent to this mu hat I of P.
No, but if you're going this way, and if you're pushing forward, you need to push forward using alpha minus S.
But that's what does doing the alpha S.
Or it could be but go backward, I guess, maybe.
Yeah, if I put the star upstairs, then it should be okay, I guess. So okay, yeah, probably we should let's agree in some notation, okay, and hopefully it's the standard. So if f goes from x to y, we define, and mu is a measure on the y, and f is just continuous. F continuous, then f star mu applied to a. Okay, mu is a measure on x. Very good. Now we are talking. This is mu of f minus 1 of. Now we are talking.
Measures are homological.
Yes, measures go down, don't go up. Very good. So then I was right. This is p.
No, you could keep it that way, but you could push forward using alpha negative S.
No. But I wanted to go that direction, so I'm good then.
Okay.
And then this is p.
Yes.
And then this is the measure here. Okay, good. And then let me go back to here. Yeah, it was correct in the beginning. Yeah, this formula we will fix it soon. Yeah, say Nawaf. Yeah, yeah. Yes, exactly. So, okay, but let's do that in the next step. So far, this is good. Now I do the coordinates as you were saying. So I have EI here. I have HIP, is this map. And this brings this measure into mu bar IP, which, if I wrote things, okay, I never wrote anything, so I cannot make mistake if I don't write. That's the good thing. Here I have EI as well, so this is HI alpha S of P. I have EI here, and I have this map, which happens to be L e to the chi I of S. Okay, and down here then I will have the pullback of this measure. So I have to lift this measure now, which goes in the opposite direction as all you were saying. So I have HI alpha S of P inverse star of mu hat IP. Nice. Of alpha S star of mu hat IP. Okay, so I'm just pulling back this guy here. So now I can erase our formalization here. Now this happens to be, and I can keep the symbol, mu hat I alpha S of P. And when I pull back this guy here, we know that this goes to mu bar I alpha S of P. And when I do this formula here versus this formula here, what I get is that this guy is, so this left-hand side is nothing but L e to the chi I S star mu bar IP. So at the end of the day, I can erase this, whatever it was, and put the outcome, which is mu bar I alpha S of P, and then I know that the implied constant is still the same implied constant, and I have an equality. Okay, sorry for the mess, but you just need to follow the diagrams, and they should tell you what. And I put the constants where it should go, I guess. So yes. So I have this family of Rudolph measures satisfy this property.
So the bars are on the linear space?
Yes, the bars are on the linear space. I don't know if this is good notation actually, but the bars are on linear spaces. So mu bar IP are on PI. Now, now comes a very important observation. Well, there are more than one more important observation. I probably can do it here. Let's go back to the Machine ergodicity. Okay, so take S in the kernel of chi I and assume alpha S, so mu is alpha S ergodic. So mu is ergodic for the whole alpha action, but it doesn't imply at all that it will be ergodic for any element of the action. Actually, there is a theorem by Pugh-Shub that tells you that it's ergodic for a lot of elements of the action. Actually, you remove some countably many subspaces, and it is ergodic for all the remaining guys. But here is a guy that belongs to a very special subspace, and there is no reason why this guy will be ergodic. And we will never prove ergodicity until the very end. So after you know everything, so then it's useless to know ergodicity, actually. So that's the magic of Katok-Spatzier. But anyway, let's still assume that it's ergodic. Now, since I'm moving in the kernel of chi I, then this linear map is just identity, because this is 1, and multiplication by 1 is nothing. Okay, so this L of that stands for multiplication by this number on this EI. Maybe I should say it, L lambda is L lambda B is lambda times B. Okay, so which means that for that S, I have that mu hat alpha SP I is equivalent to mu bar IP for almost every P and for every S in the kernel of I, of chi I.
So when you say mu is alpha of S ergodic, do you mean the flow?
Yeah, well, okay. Let's just fix this S naught. It doesn't matter, as you said. So, and then I put the S naught. This would do. Now this mu bar I sub dot goes from M alpha into this space that happen to be projective radon blah 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 of EI. Now this projectivized radon of blah 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 is a Borel space, as nice as Borel space as anyone else, with coming from some sigma-algebra, which is a beautiful sigma-algebra. And what is important is that it's a countable space. Actually, that M alpha is a countable space. The target, you also want countability, but this is countable as well, because EI is the reals actually, but well, it's a metric space with second countable metric space. The radon measures on these guys is a second countable metric space. The projectivized guys is still second countable, and the Borel sigma algebra then is countably generated. So I have this measurable map from this countably generated space from M alpha, and I have that this function is invariant by alpha S naught. And hence ergodicity tells you that it's constant. So typically one uses ergodicity for real valued functions when you claim that any invariant function is constant. You are thinking of real valued function, but actually it doesn't matter it's real valued. It only matters that the target space is equivalent, Borel equivalent to the reals or to the interval for that matter. Okay, and to be equivalent, Borel equivalent to the reals, that's what you need to be. Is a second countable blah 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 blah. Okay, so that the sigma algebra, actually you don't need any topology. You need that the sigma algebra be countably generated. That's all you need.
So in that graph there, you fixed the S0.
Here I fix the S0. Here this dot is the variable P in M alpha. So assuming ergodicity, so all this discussion I don't need ergodicity, but once I assume ergodicity, I get that these guys mu r IP, they are equal to some mu bar I for almost every E. Just one big given measure. There are no two measures here. There is only one conditional measure. Of course, up to all this, well, up to some constant, no? So this we still have to keep the up to a number. The normalization may change, but the measures are always the same.
So this projective-wise Proudhon business, it's just equivalence classes.
Yeah. Where two multiple guys, you assume they are the same.
If two measures are, if they share the measure zero sets.
No, if they are the same up to a multiple, it's really projectivized. Because the more common relation is they share the same measure zero sets. This is a very restrictive relation. So this is even more restrictive. So it's just projectivized. You think of these elements Radon measures as vectors, and you projectivize this vector space by saying if two guys are one a multiple of the other, you consider them the same. The same way you in R3 you get RP3. That you do in any dimension. There is no difference. Of course, there will be difference if you really want to look carefully at the topology of this quotient space. Then you will land into the trouble of infinite dimensional vector spaces. But here, from the Borel point of view, it's really not a problem. And actually, even from the topological point of view, it's not so much of a problem.
So here, do you need the Ci cycle to be bounded away from zero?
No, you don't need it for any of these arguments. Because again, it's just for the measurable structure. But in the argument we are going to do later, it will be important and useful. But again, there is where this remark I made of I have this very special expression for this guy will be very useful. Because when I stay in a losing set, these numbers will be bounded away from zero, these numbers will be bounded away from zero and infinity, and so this guy will be very bounded, and I don't need to care. So yeah, let me erase next blackboard and let me finish the proof, okay, under this assumption of alpha of S naught being ergodic. Okay, and remember what we are proving? We are going to prove that this mu bar I is Lebesgue. That's what we are going to prove. So it's we have this S naught in chi I, so we can always pick it, but we have no idea why it will be ergodic, and we are assuming it. And at the end of the day, I will not remove this assumption. I will modify all the proof to get rid of this assumption. So in a sense, I will force it to happen, but not using ergodicity, but using the ergodic decompositions and playing that game. Okay, so if you want, one thing that I'm not going to do, but you could do, is take mu bar, do the ergodic decomposition of mu bar with respect to this alpha S naught, take conditional measure of the ergodic component of this guy, and now do this argument with this ergodic component. Now, the conditional of the ergodic component, it may or may not be the same as the conditional of the original measure. So you have this decomposition as the mu bar measure as the integral of the ergodic components, and then this mu bar I will be the integral of the corresponding decomposition. And then you can go and argue there. It's almost useless unless you know something else, and we are going to discuss this after we understand what's the next, so how to finish even the ergodic situation. So yeah, let me try to finish in the ergodic situation.
So this statement that you cited about if you have one, so for one S naught, it's ergodic for many of them.
Yes.
So
it's not for, well, for one in particular, for many, but their assumption is the total group is ergodic, then individual elements are ergodic for a lot of them. And in particular, if you are ergodic for one, then you are ergodic for all, and then you are ergodic for many.
But then, if you don't have ergodicity, then does the ergodic decomposition? So if you decompose,
there is where starts the problem. So if the total action is not ergodic, you can do ergodic decomposition for the action. But here is a very important game here, and that's a very important observation. I take this mu bar measure. Let's say it's not ergodic for alpha S naught. Then I do ergodic decomposition. Now, the ergodic components will not be invariant by the action. They cannot be. Okay? So they are invariant by alpha S naught, but not for the other elements of the action. Actually, the action acts on this ergodic decomposition and permutes the guys. Okay? So this adds to the game and is nice. Some things can be done using these ideas, but well. And while I erase, let me tell you that after we finish with this proof, we are going to do it again, but doing the exercise of extracting, being minimalistic, and extracting what is the only things we really used about the actions and the properties to try to make a completely abstract statement about measurable dynamics, measure theory, and what do I need to prove anything. Okay, so I have these measures mu bar. So let me keep the mu hat IP because this allows me to see in the picture what's going on. Oh, one more thing that is important, and again comes from the very original statement and from Brooklyn decomposition, is the next lemma. Yeah, let me erase here. Is that there exists a set R of mu bar of R equals to 1, so a set of full measure, such that if P and Q are in R and Q happens to be in the Wi of P, then mu bar IP is equivalent to mu hat IQ. So the conditionals are the same up to a multiple if you are in the same leaf. Okay? And that again, if you think on the proof, you take the atom of the partition, and the atom of the partition, so the measure for Rocklin, for probabilities, for measure of partition, the measure only depend on the atom, not on the point. Now we, of course, are making this increasing game, and the way you are taking the limits may depend on the point, but this is just affect the multiple, so by a number, not the actual measure. So this is...
R is a regular subset in M alpha, is it?
Yes, yes. It's the place where the Rocklin theorem, so it's the full measure set which gives you Rocklin essentially, because the mu alpha, these mu IP measures are only defined as a set of full measures after all. So this, and I also want the outcome of this with respect to the mu bar measures. So this implies that mu bar IP is some TP, well, equivalent to some TPQ star mu bar IQ, where TPQ goes from EI to EI, is a translation I guess if I'm putting it here, I should put QP. of B is B plus some TQP, which is some translation that actually brings P to Q in when you go to the corresponding coordinates. And this follows from the definition of HEI and the property, one of the main properties of the HI we saw, which is that the change of coordinate HIP composed HIQ inverse is this TPQ. Or actually I should do QP, but doesn't matter. And I said it's QP, so this is QP. Okay. So now that we have this,
so later we're going to use this Q as this limit point in the imagine. So we had this P in the fiber, and you move around, and then it comes arbitrarily close to Q in the
actually,
same fiber. And then
yes, that's what's going on. I will not need to use it at all now, but that's exactly what you said was happening. The Q you are thinking, so yeah. So what is happening in real life is what you just said. Here is P, here is Q. Then I iterate here by alpha of L S naught, and I approach this guy. And then I go to the limit. I will not need to do it. And I will show you in a second why I will not need to do it. But that's essentially what is going on. Yes?
So this is something like a dynamical Lie bracket.
Yes, it is, but it's Lie brackets actually is more powerful than this. We are actually even going to have to use some Lie bracket games later. It's a second side to these techniques. Is more to the point to this game. So, but yes, there is this sort of. So the point is that if you have two vector fields, let's say you're in dimension 3, you have two vector fields that they don't commute, and then you can reach any point using these two vector fields, and that's by doing brackets. Okay, so that's the standard game. You have the bracket between these two guys, give you this direction, then I do this, and I reach any point here, and then I reach everything. So that's the magic of brackets being non-zero. So this is a very robust mechanism, which when you put together with some dynamic phenomena will help you to do a lot. Now this is a little bit more similar to a different type of statement, which is, let's say these two guys now commute, so you don't generate anything, so you don't generate a third dimension. But if you are in torus T3 and this plane is irrational, then you still get close to everywhere, and you are even ergodic. So even though you cannot reach another point, you can get very well distributed on the torus T3, and that's this ergodicity type of statement. So it's like acting transitively in the group sense, that where you can actually reach the point by the group action, or by just acting transitively in the more dynamical terms, where you can get closer as close as you want to the points. Okay, but anyway, so this is very philosophical. So here, this is just much more concrete what we are doing. So I said that this is the picture behind, but we are not going to use it. So as I said, let me emphasize, assume alpha, that mu is alpha S not ergodic. Let mu bar I be such that mu bar I is equivalent for mu bar almost every p. That's ergodicity. So we saw that this function is invariant. That's regardless of ergodicity. Ergodicity then tells me that this is constant. So let's say on a set R1, mu bar of R1 equals to 1. And then let's see what I do if I put these two guys together. So I take P and Q in R inter R1, Q in W1 of P, in Wi of P. Then I get QQP of mu bar star I is equivalent to mu bar I. Okay, because this guy is just TQQ of mu bar I, and this guy is mu bar I. So I have that this measure is invariant by this translation. So we know what happens with measures invariant by translations. Okay? Now, let G be all the T's translations such that T star mu bar I equals to, is equivalent to mu bar I. Now claim 1, G is a closed group this requires a little bit of work, it's almost a triviality. So let me see how we are doing on time. Okay, I don't have infinite time. So probably will go back to this group next time, and then I will prove this claim 1. Claim 2 is a universally known corollary of claim 1, which is G is equal to, or isomorphic, well, equal to R alpha times Z for some alpha positive 0. So these are the closed subgroups of the reals. Claim 3 mu bar I of G complement is 0. So the measure is support on this group. Okay, so corollary, and claim 4. Claim 4, if G equals to R, then mu bar I is the same as, well, I'm abusing a little bit of language, I'm very sorry. So when I say G equals to R, I'm making the following identification. Translations on the vector space EI is isomorphic to EI, which is isomorphic to R, and this is all through some identification. And then I'm using the same identification for what I'm going to denote here. Then this is e to the ct dt for some c. That's what happens if G equals to R. Claim 5. Otherwise, so if J is different from R, then mu bar I is atomic. And that's, so all these terms are really very simple exercises. Okay? So, well, 1 implies 2 is a 100% triviality. 2 imply, so 3, maybe we will have to work a little bit using this property. And what is R1, R2, and blah, blah, blah. Claim 4 is a nice exercise. I have done it more than once, and I like it, how it goes. Claim 5, again, is a triviality, just followed from the fact that these are countable sets, and a measure supported on a countable set, it has to be atomic. And then this is essentially the end, because if mu bar I has atomic measure there, it means that mu bar IP, or mu hat IP, is atomic for almost every p. And this implies that if I take now a different element of the action, which makes the Wi the expanding direction and the other direction contracting, it means that the entropy of mu bar is 0 for this other element of the action. Okay? And actually, with a little bit more of effort, not too much more effort, I can actually show that the entropy is 0 for all the elements of the action. And that's why one is assuming that there is one element of the action that has non-zero entropy. Okay? So we are going to discuss this with more detail on Friday. Okay?
Before we finish, what was R sub 1?
R sub 1 is defined here, is the set where this function is constant. So you know that this function is constant almost everywhere. Well, there is a set of full measure where it has this value. There is a claim 6, or actually a claim 4.5, which is that actually C is equal to 1. Equal to 0. So what you get is that this is actually dt. And there are several ways of proving that, really a lot. There is a very geometric one, which is very nice, actually very nice even for abstract dynamics or smooth dynamics, which is that if C is the following observation: if C is positive or negative, for that matter, if C is different from 0, let's say positive, then the positive side of R has infinite measure, but the negative side of R has finite measure. Now, this identification makes R the same as the EI, which is the same as the WIP. And the measure mu by R is the conditional measure. So if C is not 0, it means that half of the unstable has infinite measure, but the other half of the unstable have 0 measure, finite measure. And that essentially cannot be. Okay? So actually it doesn't make sense, and you can quickly prove that it's impossible, that only half of it. Okay, that's it. So what we are going to do on Friday is prove all these claims, and then we are going to go back and get rid of this ergodicity of the alpha S naught. Okay, and we will, yes.
Kind of bothers me a bit that with your definition of the displacement flow, it was not obvious for me that you can find, you don't get expansion with the constant kind of rate.
Actually, you do. You do in this coordinate. You get expansion with the constant rate. So it's not just a Lyapunov exponent type of expansion. It's independent of p. You don't need it, but you get it. If you don't have it, you have to work harder. It's more painful, and really it gets, eventually, if you want the full general situation, it gets very hard. But here you do have it, and here is the reason. But I agree with you that one has to be careful. I was not careful enough on that, but here is how you do it. So you do it through making a very careful choice of Lyapunov metric. Okay, and in this case, you can really do a very careful choice of Lyapunov metric, which is coherent everywhere and nice. And that's because you come from an algebraic situation. So you have this R2 times R3, and actually the action originally comes from doing these identifications. So you do this equivalent to Tx. So you have this identification on one hand, and on the other hand, your action is nothing but T plus S x. Okay, so alpha S of Tx is just this. So that's how suspension works. And then it's very hard to see the actual expansion here as you are complaining. Now, now you do a very geometric construction, which, again, you should think of this as Lyapunov metrics. So what do Lyapunov metrics? It spread along the orbit the contraction or expansion you are seeing from time to time. And here from time to time is until you cross the lattice, you don't see an expansion, because that's what identification. And then I really want to spread it out all the time. So I see at any given time S. So how you do it? Here is very simple. You have your let me still call it alpha. So for this, I need really the positive eigenvalues and blah, blah, blah. If not, everything is a disaster. So I have this guy, but these guys actually come from an R2 embedding into SL2R, which is just doing, if you want, A to the T, B to the S. And since A and B are diagonalizable with positive entries, this can be done very easily because you can do it for diagonal and then use the conjugacy to bring it to the A and the S. So then you have these guys. And now you define a map H from R2 times R3 into R2 times R3. And it's really R2 times R3, not the torus T3, but R3. And is H of Tx is, okay, now I need to do things carefully, is T, okay, this T is not the same. So T1, T2 are the coordinates of T, actually, okay? So you put T in the first coordinate, but in the second coordinate you do alpha of T, probably inverse of X. And now I do this change of variables. Okay, so instead of looking at these guys, which are the original identification and variables, I apply H and I look on this other side. Now this change of variable is doing nothing in the time, but it's distorting this R3. So it's changing the Riemannian metric actually of R3, and the way it distorted is exactly in a way that at the end of the day will spread out the dynamics at every iterate. So there is actually, if you do the conjugacy, then the alpha hat S of Tx now becomes T plus S, and if I did things correctly, it will be alpha S, or maybe alpha S inverse. So that's the dynamic you are going to see now, which now you actually see the diagonal matrix acting everywhere. Now, what is the problem, which is not actually a problem, is that you want the dynamics on M alpha, not on this universal covering. Now, this is not a problem. You use H to take these deck transformations appearing here, you take them to the other side. Now, from the geometric viewpoint, what you have here is a torus T2 in the base and torus T3 on the fibers. Now, these torus T3 on the fiber are all round standard tori, which all look the same. When you look at the other side, from the geometric point of view, you have T2 in the base, but now the tori in the fiber are not all the same modulus. So the lattice is changing from fiber to fiber, so sometimes it's thinner, sometimes it's larger. But since life is nice and you have this alpha of n, which maps the lattice to the lattice, so this still is good and is coherent. So you are changing the size using this alpha of t in the meantime, just to reflect, as we were saying, just to reflect, instead of waiting until you cross the fundamental domain, you spread it out all the time. Yes, it is a time change, but it's not, it's a trivial time change, but still is a time change. So then if you use the Riemannian metric coming from here, you see that what you are doing in the space EI is exactly multiplying by e to the chi I of S. And that's it. So, but again, this can be done because you're in this very beautiful algebraic situation, and more important, you have this extension. So this extension makes everything. And this should be 3s, not 2s, but anyway. So if you don't have this extension, which there are situations where you don't have this extension when you work with more general groups, then, well, then you have to suffer more. Still, this can be done pretty reasonable when you are with some sort of algebraic situations. And if you are in purely smooth dynamics, then you only have Lyapunov exponents. And then if the bundles EI are continuous, you can control the cocycles playing some games. If the EI bundles just come from pacing theory and they are just measurable, you have really to suffer more. And that's what we did with Katok and Kalinin. We do some reparametrizations, which made the chi I constant. But you have to pay because these reparametrizations are, so as Alp says, so these are some sort of time changes. In this other reparametrization, time changes in motional situation, they are just measurable, they are not trivial, and then you end up with some, instead of smooth dynamics, with measurable dynamics. And well, you win that the exponent is now constant, so really you are doing chi is independent of the point P, but now your dynamics is not more smooth, it's just measurable dynamics. So then, well, you have to play both plays at the same time. So when you need smoothness, you go to your smooth situation. When you need the chi I to be the chi I, you go to your non-smooth situation. That's how you do. But yeah, here, that's how you get rid of this problem. And when we are going to use it, because we are going to use it for the SLNR action, for the G action, then this will be even more natural. Okay? Because things will be happening actually along the group. So this is something that I hope I get to make you understand what's going on. Because here we have fiber where the dynamics happens and the group, which is just the time. When it comes to go back to normal subgroup theorem, everything will happen along the group. And dynamics on the fiber we will never be seen. And what is magic is you don't need to know what is your fiber and what's going on there. So you only care about your group. And which here was useless, the group. But in that situation, everything will happen there. Okay. So we continue on Friday. Okay? Okay. So let's go back to where we stand. So we have here our two matrices, our M alpha, the Veil chambers with their kernels of the Lyapunov exponents. We have the measure mu on M, which we leave to the measure mu bar on M alpha. We have our WIs, which are tangent to the EI. parametrizations hi p from ei to wip. We have the disintegration p into mu hat ip. This mu hat ip is a radon measure on WIP, and we have also the mu bar IP, which is the guy related with this dr h pi I star mu bar I equals to mu hat IP. That's just the definition of the mu bar. So we have mu hat IP here and mu bar IP here. Yes. Okay. Now, so that's all the structure we care. We have a lot of uniqueness of these guys up to some multiplication constant. So we had this property that if Q is in, well, there exists a set R, mu bar of R equals to 1. Oops. R contained in M alpha of full measure, so that if Q belongs to Wi of P inter R, then mu bar, so mu hat IQ is pretty much the same as the mu hat IP, so up to a multiplicative constant they are the same, and as a consequence we have that in particular T PQ star mu bar IP equals to mu bar IQ, where TPQ of B is B plus some translation. So that's one big property of this guy. The second big property of these guys, which I will write it here, is that if I take, so for every S in R2 and for every P in the same set R, if alpha S of S also belongs to R, then which actually I could have assumed. It's very useful eventually. Maybe we will discuss it later. There is a way of modifying stuff so that we can assume that R is alpha S invariant for every S. But it's not really so important in what we are going to do. So let's keep on this way. So then L e to the chi I S star mu bar IP is mu, what is the equivalent up to a multiple to mu I alpha S of P. So these are the two, and here I put an equality, and I always made this mistake. So these equalities are only up to a multiple. Okay. So these are the two main properties, and actually that's essentially all we need for the rest of the discussion. Now we take, as we said before, S naught inside the kernel of chi I, S naught non-zero. And now I will do something that we were not doing before, which we will have to bypass in a different way, simpler way in the case of the Margulis normal subgroup theorem. In this situation, it's harder than in Margulis situation, but we will see it later. What's the difference? So I don't want to assume that alpha of S naught is ergodic now. Okay? So I need to do something about this. I have this mu bar measure, and I don't want to assume because I don't know this measure is ergodic. So I need to do something. So then we are going to discuss partitions. So here are the 4 most important partitions that will take place in this game. And actually, 2 of them will coincide, but actually all of them will coincide eventually. But anyway. So partition 1. I call it epsilon S naught. Epsilon is for the E, and E comes from ergodic. So is partition into ergodic components. Okay, and I will try to be reasonably detailed in this part today, because really being able to play with all these partitions will be very useful in all that comes later in this course. So ergodic decomposition typically is taught in the ergodic theory course as you write your measure as an integral of measures which are ergodic. So this is not the best approach, at least not for this, and I don't think it's really the best approach in ergodic theory. So the best approach in ergodic theory is through partitions. So maybe I should have made one observation here, which is an equivalence between measurable partitions and sigma-algebras. Mu almost everywhere, and again mu almost everywhere. Okay, well, mu almost everywhere means, again, you have to restrict to some set of full measures and blah blah blah. So this is this identification works very well in this almost everywhere situation. In the if you can do it without the measure mu, actually, but for this you have to be very careful in this arrow, because for every sigma algebra you want to have a partition, and for every partition you want to have a sigma algebra. So for every partition you have a sigma algebra, that's very easy. The fact for every sigma algebra you have a partition, you also have it, and that's the definition of measurable as soon as your sigma algebra is countably generated. And that's, in a sense, is the definition of a measurable partition to be measurable. Okay, we say almost everything becomes a little bit simpler in the sense that everything will be countably generated almost by definition if you are putting a measure mu, which is on a metric space and it's a probability measure. So, and your sigma algebra is sigma algebra of the Borel sigma algebra.
Is it true that Lebesgue spaces are precisely those spaces for which this correspondence works?
Essentially, yes. Yes. When the measure mu is so when things are equivalent to the interval 0, 1 is where this correspondence goes. Okay, and these atoms of this sigma algebra, so well, you have to be careful, because when I think from this sigma algebra point of view, then these elements of this partition, which are the atoms of the sigma algebra, are not points, are segments, or, well, are sets. And these are the sets that need to be collapsed to a point. because the sigma-algebra is not able to distinguish between them. Not anyway. So okay, so how we define this partition? Okay, so I will give two definitions of this partition. Both definitions coincide, not only because of this arrow, but there is something substantial behind as well. And there is all theory of martingale. There is a lot of philosophical discussions of what's going on, but we don't need to go so far. So definition one, I have the sigma-algebra, which is all the sets A, Borel. And I know the matrix is A, but A for a set, I hope we don't mess up. Borel A contained in M alpha such that alpha S naught of A equals to A mod 0. And this is a sigma algebra. It's a sigma algebra of invariant sets. Okay, ergodicity would tell me that this sigma algebra is trivial, modulo 0, but we don't know ergodicity, so this gives you a sigma algebra of sets. Now the second way, and that's the way we define the partition, I need to say what is the atom. And to say what is the atom, I will appeal to some set R S naught. Actually, I call it, let's call it Beer S naught, Beer for Birkhoff, which is a set of full measure. And then for X in this set, so I only need to define atoms for the full measure set. These are all the Y's in Birkhoff, such that the limit, and now I could use S or N, I will just use N discrete iterations, just make my life simple. So I could use flow or I could use iteration. Sum from K equals to 0 up to N minus 1, N going to plus infinity of phi yeah, let me do it this way, of alpha K S naught of X is equal to the same sum K equals to 0 up to N minus 1 phi alpha K S naught of Y for every phi in C naught, or any dense guy on L1. So take any dense set of functions in L1 and ask it for this set of functions. It should be countable, so if I want to do it carefully, I should be countable. But once you have for the countable family, then you will have for every continuous function, not for every L1 function, but for every continuous function, just by continuity. Okay, so typically you want to put a countable set here, so that for each phi you have one partition, then you have the countable intersection of this partition, and then things. Okay. Okay. In any way, this is a partition. You can check easily that this is a partition. Okay, into sets. So this a partition of this set, which is a set of full measure, and Birkhoff-Ergodic theorem tells you essentially that these two partitions, so this sigma-algebra and these partitions, are associated one to each other. Well, actually, you don't need Birkhoff-Ergodic theorem to claim that these are associated one to each other. You need Birkhoff-Ergodic theorem to claim the fact that I'm putting a limit here, and this makes sense on a set of full measure. Okay? But anyway, and then if you want to have the standard ergodic decomposition theorem, you just go and claim Rocklin theorem for this partition with this sigma algebra associated, and Rocklin is ergodic decomposition theorem. And then you can even go further and take this sigma algebra, play some martingale style of game to define this partition, and then you can see that this partition has to be characterized by this property, and in this way you use martingale theory to prove the Birkhoff-Ergodic theorem, which again shouldn't be so surprising because this the maximal ergodic theorem, which is this sort of Lebesgue density type of statement, and the proof of martingale are more or less the same, so it doesn't matter. Okay, so here is partition 1, partition into ergodic components.
So in words, this E sub S naught of X is the set of all those Y's whose orbit averages are the same.
Exactly. Exactly. Where Birkhoff average gives you exactly the same. So when I tried, so since this is a compact metric space, I could average delta along the orbit and I get the same measure.
And does it matter that you're just looking at the forward inverts?
No, it doesn't matter. I could ask forward and backward. I'm going to work only forward, but actually, since I'm restricted to this set of full measure, in this set of full measure, forward and backward inverts exist and are the same, and whatever needs to happen will be happening there. So no difference will be made. Okay, that's partition 1. Partition 2. Partition 2, we will not have this luxury. Okay, we will be harder, but still, what is important is that it is true. Partition 2. So these are measurable. All the partitions that will appear here will be measurable partitions almost by definitions eventually. Okay, so this is a measurable partition. Next partition is the Pinsker partition. And what I'm writing here, so what I'm discussing here is, maybe I should put here, is Katok-Spatzier and it has a name. It's called the pi-partition trick. And pi is because Pinker's partition is also called the pi-partition. So and it's denoted by pi. Pi S naught, because everything is with respect to this guy S naught, which has associated the sigma algebra B pi of S naught. And here what is really easy is to define the sigma algebra, yet the partition can be shown to exist, is what Pinsker does, and is one of the basics of ergodic theory, which has some properties which, when things trivialize, you get Kolmogorov. Okay, so this is all the sets, Borel, such that the entropy, this is entropy, mu bar of alpha S naught with respect to the partition A M alpha minus A is 0. Okay? So it's all the sets which generate 0 entropy. So instead of taking all invariant sets, you take all the sets that generate 0 entropy there. It is reasonably trivial to show, there are other ways to show it, but that every invariant set will contribute to 0 entropy, which means that the sigma algebra oops, epsilon is not. The sigma algebra of invariant sets is contained here in this, and this implies that correspondingly for the partition, pi S naught of X will be contained in epsilon s naught of x for mu bar almost every x. And here always we have to work with an almost everywhere because all things are only defined almost everywhere. And the notation for this is pi s naught refines epsilon s naught. Okay, and actually even though here the containment goes in this way, the inequality is written the other way because it's to reflect this sigma algebra containment. So who is large and who is small come from this picture rather from this picture, even though for me that I like to see things more symmetrical, the atoms are larger for the ergodic than for the disk. So, but the pi-partition is larger than the ergodic partition because the sigma algebra associated to the pi-partition has more elements than this sigma algebra. But anyway, so this is not really so crucial. I have this second partition, the pi-partition, which has this property. Next partition. And the third partition again is defined using the sigma algebra. Okay? And is the unstable partition. And is actually the measurable hull how do you write the convex hull? So it's H-A-L-L U. Like that?
U-L-L.
Like that?
Yes, but without.
Oh, without A. Okay. Thanks. Let's go. Okay, I think. Oh, Kenneth is the only native speaker. So if we are making too much mess, he should correct us. Okay, so this is the measurable hull of the unstable partition, actually, of the partition into unstable manifolds. So that's the word definition, and to make a concrete definition, we define the sigma algebra of this guy. So again, it's all the sets in M alpha, and before saying that the sets are Borel was not so really interesting and appealing. Here, the fact that they are Borel is crucial. Okay. Borel. And also crucial, yeah, I forget here, I'm very sorry. There is some bracket here, and also I should put them here, which is not such a thing, but let me give a definition. So this is all the sets B Borel such that B coincide mode 0 with A for some A in A. Okay, so you enlarge your sigma algebra to add all the set of measure 0. This is the completions. And this is required to have this thing here well established. Again, this is some ergodic theory. It's not so important.
Also, when you say this one partition is inside the other one, you don't mean that any atom in the left-hand side is in the right-hand side.
Yeah, it's. And actually, if you want, I should be 100% careful, and maybe I will do. So what I mean is that there exists a set R13 of full measure such that if X is in this set R13, then pi S naught X intersected with this set is contained in the epsilon S naught of X intersected with this set. Okay, so I should, in a sense, restrict to this set of full measure. So here this is a mod 0 statement. Okay, and actually
it's stronger than refining them, actually.
What do you mean? So if I apply Rocklin theorem, then this I get a measure here on this atom, which I can further disintegrate into measures here.
I thought that was a partition itself. That's why I.
Yeah, no, this is X.
It's an atom.
Is the atom of the partition. Okay, so. And yeah, everything needs to be understood mod 0 here. Okay, so because it's measured, so points do not exist for a measure. So you cannot say, I take this point. Of course, eventually you may want to do it, and that's why whenever you want really to say, I really want to take this point, that point, then you have to go and appeal and say, there is a set of full measure such that if I take the point on this set of full measure, I can do a lot of stuff. And that's how you take points. If not, everything happens me almost everywhere. And yeah, this when you say me almost everywhere, is a lot of waving hands, and you have to be very careful. If you know what you are doing, you still can make mistakes, but you have to keep track of these sets R13 that keep on popping up, saying if I take the point here, if I restrict here, if I do this thing here, which is not actually the same as doing this thing here, and this type of things. Okay. Okay, so now this is again, we'll have this generating business here. So it's all the sets which are Borel and are U saturated. Okay, such that if A is saturated by the unstable foliation of alpha S naught. Okay, so that means implies the unstable of X for S naught is inside A. So whenever a point is, the whole leaf is there. So we have 5 partitions actually, because I need the 4th partition. But the 4th partition is very quick. It's the stable partition. And the stable partition is actually, by definition, the unstable for minus S naught. Okay? The same way that the stable foliation is the unstable for minus S naught. So, so this is partition 4. And then partition 5 is the last one. which is pretty much the same as the same partition as the sub-partition, but is the partition into Wi leaves. Okay, so which is actually Wi, which again you define via the sigma algebra and is the same definition. Okay, so it's all the A in M alpha, A Borel, and A is saturated by Wi leaves. And actually, I keep on putting the S not here all the time, and I shouldn't have, because I really want to have this definition for all the S's in the world. Okay, so now the fact that I can have this definition so that I can pick this set B S independent of S is a little bit painful. I will only need it for 3 values of S, or even less than 3 values. No, 3 values should be okay. It will be finitely many values. Even if it is countable, it wouldn't make any problem because I can keep the set of full measures. But yes. Still, S naught is a very important guy for us, but I really need to know the partitions for this. Here, the inequality is in the same S. Okay. Here again. Okay. Okay, now the first good news is out of the 5 partitions, the partition 5 is independent of S, of the value of S. Only depends on the Wi guy, not on the S. Good to know. Next thing which is important to know. Here is the kernel of chi I. Let's say we are positive here, negative here. And I don't think I care any of the other guys. Now, properties. One is, as I said, epsilon S, and the notation, well, anyway, so these are small, so is by S for every S. So that's the first property. Second is crucial, which is a theorem by Ledrappier-Young. If times permit, I will go through this theorem as well. It's not so simple to prove. In the setting we care, it's much simpler than the general Ledrappier-Young theorem, because what is really hard in the Ledrappier-Young theorem is when you have 0 exponents. When you don't have 0 exponent, it really simplifies quite a bit. But when you have 0 exponent, it gets really much harder. Though in our situation, the 0 exponents come from isometries. And when the 0 exponent comes from isometries, again, it simplifies quite a bit. But anyway, what does the theorem says? It says that U of S naught, U of S, is equals to S of S, which is equals to pi of S for every S. So the pi partition, the stable partition, and the unstable partition are all the same partition. That's what Ledrappier-Young says. And this is a most important theorem in this business. And it's one of the most important theorems in smooth ergodic theory in general. the fact that the stable partition and the unstable partitions are the same, and they are the pi-partition. Okay, and the third property is a complete triviality, the same as, well, even more trivial than the first. Yeah, maybe let me push this picture towards here. Kernel of chi I, here is positive, here is negative. So the third property says that if chi I of S is negative, then Wi refines US, because that's just saying that the unstable, the Wi stays in the unstable manifold. Okay? And if chi IS is negative, then Wi refines the stable partition, because then the Wi goes inside the stable partition. If chi I is 0, we have no clue. No idea, and we don't.
But you wrote chi of S is negative twice.
Good. Thanks. Okay, so if chi of S is positive, then the Wi is in the unstable. If chi of S is negative, the Wi is in the stable. There is a fourth property, which is quite important.
When you say that Wi is the, for instance, the join or ledger, something like that, of all those S's for which chi I of S is positive? Meaning, I'm asking if
The intersection of all these guys, or, well, anyway, we have to make some choice. Let's say it's here, so you want to be the intersection of all these guys, intersection over S. Yes, you can do, and that's actually is where the theory of coarse Lyapunov exponent comes, because you have to group together the guys. So there is a linear algebra. We are going to discuss this linear algebra. And it's a very geometric statement. So this is, so property 3 is very geometric, and you start intersecting the Wi. You do it actually at the linear level, and you take these vector spaces, all the unstable spaces, and you do some linear algebra. And in this situation, you get it. In the more general situation, you have to discuss what are coarse Lyapunov exponents and coarse Lyapunov spaces, and you will have more or less what you wanted. Yes. Here in 3 dimensions, what you said is completely right, and it's not hard. It's quite trivial, actually. Because actually, for the correct choice of S, you have an equality.
right.
Okay? Now, still, what I want to do now, and that will be the condition 4, the property 4, I will pick some S naught. I will pick some small neighborhood of S naught that will have to look like that. So it doesn't intersect any of the other kernels. It only intersects this kernel. And then the property 4 tells me that given S naught in kernel, actually it has to do with the notion of Bell chamber, but I don't want to. So we define it, but I don't want to really repeat the definition. So I take this guy, then there exists B, or Bs naught containing R2, a neighborhood of S naught, such that if S is in this neighborhood and chi I of S is positive, if I take two such guys, which so I'm going to wait a second. Yes. And they have the same value of the chi I, not the same value, the same positivity of the chi I, then the W U of S1 is the same as W, and hence the U's, and hence the U of S1 is equals to the U of S2. And the same with the stables. And hence S1 S2. And same thing if chi I of S1 is negative and chi I of S2 is negative, and same if chi I of S1 is the same as chi I of S2 equals to 0. Actually, a little bit more is true. And this little bit more true is what will really make the whole magic. Moreover, so this is trivial, okay? So when I stay in this neighborhood, all the guys in this half circle up here have the same Lyapunov exponent, the same sign of Lyapunov exponents. So whoever vector was contracting, stay contracting. Whoever was expanding, stay expanding. And there is no freezing vector, so there is no problem. The same thing what happens down here, and when you are in the line over this kernel, whoever was 0 is 0, and whoever was positive stays positive, whoever was negative stays negative. Now what is also true, which is for prime, and now is what really the game starts, is that if if S1 belongs to this neighborhood and chi of S1 is negative, then WU of S1 equals to WU of S0. Okay? So remember, S0 is the guy in the kernel. And if chi of S0, chi I of S0 is positive, again S0, S2 in this neighborhood, then WS S2 equals to WS S1, and this implies that the S0, the stable foliation for this guy is the stable partition for this guy, and this implies that the unstable partition for this guy is the unstable partition for this guy. Okay. Let me explain this condition for prime. So I have E1, E2, E3. Okay? So the question is what happens. So let's say I equals to 1. Okay? Then we think on E2 and E3. The neighborhood is chosen so that the second and the third Lyapunov exponent do not change sign. So they are both positive or both negative, or one positive and the other negative, but they do not change sign. Actually, it cannot be both positive or negative, so it will be one positive and the other negative. Okay, but they will not change sign at all. So let's say the chi3 is negative. So whatever vector in the third direction is stable on all this neighborhood, whichever vector in the second direction is unstable in all this neighborhood. Now I take an element where the first exponent is negative. It means that now the second direction, which was the unstable, was belonging to the unstable in those whole neighborhood, is actually the unstable for all guys doing this, as well as for the S0. Because in the S0, I have one-dimensional unstable, one-dimensional unstable. Okay, so maybe, let me erase here and do this picture. This is chi1, this is chi2, this is chi3, and assuming that down here I have negative for the chi1, I have, let's say, positive for the chi2 and positive. I cannot have both positive chi2 and chi3. So this is chi2, and this guy here is chi3. So when I switch here, okay, that's configuration should be good. So I have minus minus plus here, I have here plus minus plus. And over here S0 is plus is 0 minus plus. I have this. So for S0 I have 0 minus plus. If I take S1, I said S1 was with the guy negative. I take S1 is minus minus plus, and S2 is plus minus plus. Okay, so now for this guy, the unstable is E3 and the stable is E2. For this guy, the unstable is E3 and the stable is E1 plus E2. And for this guy, the unstable is E1 plus E3 and the stable is E2. Okay, which is what this statement is telling us. And this is just some simple linear algebra, and in higher dimensions, essentially the same holds. Okay, so it's not really a three-dimensional picture. It's a quite general, even though you need something to happen in order that this be true, which is what is in general called totally not symplecticity, because what will be bad is if this kernel is not just the kernel for chi1, but it's also the kernel for chi4, and chi4 is the opposite of chi1, because then when I switch, two guys cross, and then I cannot have any more this picture. But this is in this three-dimensional situation, and whenever this is true, I can carry out the argument, and that's what Katok-Spatzier do.
At this point, you don't say that these S0, S1, S2 are integer points, right? They could be real points.
Whatever real, yeah. Okay, now I take S1. And I start writing. I have epsilon of S0 is smaller than pi of S0. This is the unstable for S0. Now, this is the same as, and now I come here, and the unstable for S0 is the same as the unstable for S1. But the unstable for S1 is the same as the stable for S1. That's the Ledrappier-Young, item 2. Now the stable for S1 wait a second. I need to be careful and do it correctly. No, I did the wrong. Did I read the wrong or I did the wrong? No, yeah, I did. It's still right. So this is the stable for S1. Yeah, I forgot one very simple property, but still. So the stable for S1, let's see here, is E1 plus E2. Okay. So this is smaller because it's E1 that changed sides. Wait a second. Yes, exactly. This is the picture I wanted. I'm sorry it took me so long. It was just one step. It's smaller than W1. Yeah, I forgot this is the most important property, which is property not just for prime, but actually the consequence of property for point prime, which is that if chi1 of S1 is negative, then W1 is larger than stable of S1. This is actually what I care about the 4 prime. Okay, which is that if this, okay, we were playing with WIs. Okay. Oh, actually, yes. It's property 3. Then I'm sorry, I had to use property 3. Yes, this is property 3. And now we are done. So let's see. This is property 1. This is property 2. This is property 4 prime. And this is property 3. And this is property 2 used again. Although 2 has two equalities, this equality is simpler to prove than this one, I think. But anyway, doesn't matter. Well, it depends on how. Okay, now you say, why do we care? Okay. Okay, all this was to show that this guy, the W1, which is a foliation for the whole system, but in particular for S0, is an isometric foliation. So all smooth ergodic theory, Pessin theory, Ledrappier-Young theory will tell us what happens with stables and unstables, but will never tell us what happens with the zero exponent directions. And in this game, I know what happened with these guys. This guy belongs to this epsilon of S0, which means that ergodic averages are constant on leaves of the W1. That's what we prove. So all this day was just to prove that ergodic average for S0 are constants along the leaf of W1. And that's just by definition of the ergodic partition and definition of this inequality. It means that the atoms of W1 are inside the atoms of epsilon S0. So the leaf of W1 belongs to the partition, and belonging to the partition means ergodic average are constant along W1 leaves. So that's Birkhoff theorem, actually. The fact that ergodic average are constant along stables and ergodic average are constant along unstables. But this guy is not stable nor unstable. And that's the magic. And yet I can still say the ergodic average are constant along this foliation.
So in the interaction of a diffeomorphism, this middle part just collapses. You just have that Wi is included in epsilon of S naught.
Right. No, because so in the diffeo situation, without using the suspension, I cannot make all these equalities. That's why I need to go to suspension. Because if not, I will not have this. I'm sorry. This I will have. What I will not have is this guy. And actually, I cannot pick the S naught even more if I don't go to the suspension. Right. Now, once I know that ergodic averages are constant along the Wi direction, then I don't need to anymore to ask the alpha S naught to be ergodic. Because remember why we care the ergodicity of alpha S naught. It was for recurrence. So I took the P here, and I wanted to move to the Q in the same leaf. I wanted to flow or iterate and be able to return here. Now, the fact that this Q is in the same ergodic component of P tells me that this is possible. Okay, then that's simply because I take a very small neighborhood of this guy. I take Birkhoff average for this characteristic function of this open set, and then ergodic average for this guy tells me that, well, they are the same for P and for Q, and I'm returning there. Pretty much what is telling me. And we are very over time.
Okay, can I just have a question here? So basically, the main thing is that, okay, so WI is not, it's basically a center for it, it's not, right? WI.
So it is a center. It's a center for the S naught direction. Exactly, and that's what we play. The game we play. That for other guy it is expanding, and then you have this. So you have this game here that it is, well, in this case is contracting for this other guy. But then this is this magic that I can swap this to this, and this is really magic. Okay, so it's true, it's ergodic average are the same for the future and for the past. It's some sort of Hopf argument, but your measure is a very ugly measure here. Okay, and then this tells you that this equals to this guy, and then the second magic appears, which is less surprising, that is the unstable for this guy is the same as the unstable for this guy. And then this inequality, again, you can forget about this part and just use the fact that Birkhoff averages are constant along unstables to have this inequality. So the real magic, in a sense, is happening in here. So it's really some sort of Hopf argument. And of course, the fact that this is true. Even though the fact that this is true is not such big deal. The fact that this is true is quite a big deal. Yeah. Yes. Yeah. Yeah, so this still doesn't solve anything. So this is just how to bypass the ergodicity. So then we have to finish the argument. It could be that the conditional measure here is atomic, and then all the argument we are doing will be empty. So you will want, that's why you want the positive entropy assumption to make sure that the measure here is not atomic for the correct choice of chi I. And once that the ergodic, the conditional measure is not atomic, then you are done. Actually, let me use one last minute and then we just quit. So the way we are going to use, because it's very useful to do it this way, actually, even though you can do it in several other ways. So we have this mu hat I measure, the conditional measure, but we could take the mu s naught hat I. So mu s naught is one ergodic decomposition. Okay, so you take one ergodic component of the measure mu, or mu bar, and the whole point is that these two measures are the same. That's the outcome of this property. So if I take ergodic component for the measure mu, and then I disintegrate further for the wi, is the same as disintegrating further for wi, because what we are doing here is you disintegrate for this, and then this disintegrate for that. So disintegrating is respect the order. So then, yeah. So this is Ledrappier. So is a very smart usage of Ledrappier-Young, which is this property. Plus, no, not this property. This property. Yeah, maybe let me use another 30 seconds to tell you why Ledrappier-Young is. So this, why this is supposed to be true, and why without zero exponent you essentially can make sense of the following proof. So you take the Bowen ball, the positive Bowen ball. The positive Bowen ball is the approximation of the stable manifold. If you do it on the point x. Now, if you take f minus n of this is the negative Bowen ball on f minus n of x, which is an approximation of the unstable manifold for the guy. Now, this approximation of stable manifolds is going to give you this guy. Now, recurrence plus the fact that this is stable manifold plus invariance will tell you that this is the same as that. Okay, which is the same thing as the proof as the Birkhoff average for the future is the same as Birkhoff average for the past. But now you need a little bit more, because at this level you will have to make some sort of entropy consideration to make sure you are not losing information when you play this game. And that's what it really will give you equality between these two partitions. But that's what is behind. That's why it's not so surprising. Okay, now the problem when you have zero exponents is that this is not actually an approximation of the stable manifold, because you have the zero exponents still around there, so you need to play a lot with the epsilons, get rid of stuff, and things start getting uglier. But if you have, for instance, an Anosov system with measure with product structure, now this is almost the trivial proof of this thing. Okay, so what we are going to do, one question for all of you. Monday is, are there classes or not? Because it's supposed to be President Day, but I don't know how. So we can have, I don't have any problems, so I come here. Okay, so I come on Monday unless someone has something to say, and then we have. Good.
We're recording stuff.
We are all recording anyway. Okay, good. Okay, then see you on Monday. Thanks. Bye-bye.